Hello and namaste everyone. Welcome to lecture 10 of this NPTEL course on stochastic approximation. So just a quick recap of what we have been doing. In this week we have been covering some basics of measure theoretic probability. In particular, we have been defining some concepts, making you familiar with certain notations and definitions so that we can talk about conditional expectations, and in the following week we can talk about martingale differences and their convergences. Is that okay? So let us do a formal recap of what we did in our previous class, right. So in the previous class we introduced this concept of conditional expectation. In particular, we said that if you have a random variable x and a sub sigma field g, then this conditional expectation is another random variable with the property that this new random variable is g measurable, right, and it approximates x in a certain sense. In particular, we require that these two numbers be the same for every g in calligraphic g. So what is the left hand side? Well, the left hand side, as we have described, is the expected value of x indicator g. This is the left hand side, and the right hand side is expected value of this new random variable, expected value of x given g, right, times indicator g, right. And we require that this new random variables expectation with respect to g, or the expectation of the product of these two random variables with respect to g should be the same as the expectation of x times indicator g for every g in calligraphic g. So this is what do we mean by that the conditional expectation approximates x. Whenever we say that, we mean precisely this, that instead of taking the expectation of x times indicator of g, you can take the expectation of the conditional expectation times indicator g, right. So these two things will be the same, and these two things will be the same as long as your g belongs to calligraphic g. So this relation will not hold or need not hold outside this calligraphic g, okay. So this was what we discussed last time, and I had posed two questions with regards to this definition. One was what's the intuition behind this definition, and we had looked at a very simple case and used that to illustrate what is this conditional expectation talking about, and so on and so forth. And there was one thing that I forgot to explain in the previous class. I had said that sorry, not this, but I had said that your conditional expectation in that special case, okay, this thing equaled almost surely this infinite sum that we have, right. So in that example that we had discussed, I had indicated that this almost sure equality holds. So let me first recall the relation that we had written, okay. Now the question is, why did I write almost surely equal? Well, you have one random variable over here and one random variable over here, and if you look through the this probability part textbook by Resnick, you will see that if you have two random variables, let us say y and z, which are almost surely the same, which means that probability y not equals z is 0, right. So let us say you have two random variables y and z, and we will say that y almost surely equals z if a probability condition like this holds, that is the probability that y not equals to z equals 0. Now from the properties of expectation, one can show that even though y and z, right, can be different on a 0 measure set, their expectations will be the same, okay. So expected value of y equals expected value of z, right. So coming back over here, why did I write almost sure here? It basically means that except for a set of measure 0, these two things could be different, but whenever you exclude this 0 measure set, these two functions should be identically same, right? And why do we insist almost sure? The reason is just that someone can change this right hand side on a 0 measure set and conclude that, oh, this is not equal to what you have written over here. So this is just to safeguard against that such a discussion. It is to ensure that, okay, you can change this right hand side over a set of measure 0, but apart from that no one would be able to change this beyond it. Okay. Alright, so this is something that I think I forgot discussing in the previous class. There was another question that remained unanswered from the previous class, which is that of why should such a conditional expectation exist, right? So conditional expectation, recall, is a random variable which is G measurable and satisfies these two properties. So why such a random variable, basically this thing, exist? Okay. So while I won't be able to give full details, however I can give enough details so that if you are interested in answering such questions, okay, you have references to things that you can read and study on your own to figure out what is the answer. Okay. So the existence of such random variables are guaranteed thanks to this theorem called as the Redon-Nikodym theorem. I should write M over here, Redon-Nikodym theorem, and you can look at theorem 10.1.2 and corollary 10.1.2 in this textbook called A Probability Path by Resnick. So if you look at those theorems, you can indeed get access to the details of this Redon-Nikodym theorem, and in particular how this theorem guarantees the existence of this conditional expectation, right. So if this was a course on probability, I would have given you full details. However, in this stochastic approximation course, I am just trying to give a quick overview of this these concepts, and hence I am only providing you a reference, and I encourage you to look it up if you are interested in knowing details about this existence. So in the remaining part of this lecture, we will discuss some key properties of conditional expectation that we will be repeatedly using throughout our discussion on stochastic approximation. Okay. So the first of these properties is the linearity property, okay, and I would like to emphasize that for a small subset of these properties I will tell you how to prove, and in some cases I will in fact prove it also, but for most of them I won't have the time to provide exact details of the proof, and I encourage you to look at chapter 10 of this textbook called A Probability Path by Resnick. So he would have provided you with all the details. Alright. So the first property that we want to look at is that of linearity. So what does the linearity property say? It says that suppose you have two random variables x and y, let us look at their linear combinations, right. That is alpha x plus beta y, where alpha and beta are real numbers, and let us look at the conditional expectation of this random variable, right. And the linearity property says that the conditional expectation of this property would equal alpha times the conditional expectation of x and beta times the conditional expectation of y. Again, this equality holds in an almost sure sense, in that apart from a set of measure 0, you cannot change this right hand side. Okay. Alright. So I will not be giving you the proof, but the proof is very straightforward. It follows from the linearity property of expectation that we had stated before. So you just invoke that property and verify the two conditions that were there in the conditional expectation definition, which is that the right hand side should be G measurable, and if you take the product of this right hand side with indicator G and look at its expectation, then that expectation should equal the expected value of this alpha x plus beta y random variable times indicator G. So whenever these two expectations hold, that will hold from the linearity of expectation, and one can conclude in that case that this indeed plays the role of a conditional expectation. Okay. So the next property, while it is very trivial to state, is often very important. What this says is that suppose you have some random variable x, right, and you have been given a sigma field G, and suppose it turns out that the given random variable is measurable with respect to G, right. So the given random variable itself is measurable with respect to G. In that case the conditional expectation of x with respect to this sigma field G is basically x itself apart from a set of measure 0. Is this okay? So that is why I have written AS over here, right, and this makes sense, right. What is conditional expectation? Well, it is the best G measurable random variable, right. Now if x itself is G measurable, then that will be the best proxy for x, right. And I would like to distinguish this case with what we have seen so far, right. In what we have seen so far, we had some parent sigma field f and x was measurable with respect to f, and your G was basically a sub sigma field defined with respect to f, and we were looking at conditional expectation of x with respect to this G, right. And in this special case what we are considering is that the given random variable x is measurable actually with respect to G itself. Is this okay? So of course since G is a subset of calligraphic f, if you are measurable with respect to G, you automatically become measurable with respect to f, but measurability with respect to f need not imply that x is also measurable with respect to G. So in that sense this is a special case. So if you have measurability with respect to G, then one can very easily check that expected value of x given G is actually x itself, alright. So now let us move on to the third property. The third property looks at the case where your the sigma field with respect to which you want to define the conditional expectation is trivial, in that it only includes the empty set and the sample space omega, right. And in this case the claim is that the conditional expectation of x with respect to such a G will actually be a constant, and it will be the actual expectation of x itself, right. So when you take the conditional expectation of x with respect to G, it is a constant expected value of x, okay. And since this is a very easy proof, I will verify this over here so that you know how to verify some of these results, right. Now the first thing we need to verify is that this right hand side over here is G measurable, right. Now so let us define a function y which is equal to expected value of x for all omega in capital Omega, right. So and because of this definition one can see that y inverse of any set A which is a subset of R, this will either be the empty set or omega. Is that okay? And when it will be empty set, if you know your set, okay, or let me write it the other way, that expected value of x which is a real number, okay, this does not belong to A, and on the other hand if expected value of x belongs to A, then y inverse of A will be you know omega. And in this sense you can see that this constant thing that we have on the right hand side is indeed G measurable, because the inverse of any A is either the empty set or omega. In particular we can conclude that y inverse of B of R is actually G, which is what is given over here, okay. So this is G measurable. So we have verified the first condition in the definition of the conditional expectation. Next we have to verify that for every set G in this calligraphic G collection, okay, the suitable expectations are take the same value. So let us check that. So for the case where G is the empty set, okay, so for the case where G is empty, right, in that case we have to take the conditional expectation, right, and we are claiming that this conditional expectation is actually expected value of x, okay. So we have to you know check that that this thing over the empty set actually equals integral x dp over the empty set. So we have to verify this, and again as I told you, the right hand side is actually expected value of x, you know, times indicator of this set, but since this is empty here, right, this is actually 0, right. So x times 0 is actually 0 and expected value of 0 is basically 0. So this can be checked via this definition of the simple function, the expectation of a simple function that we had looked at. In particular, this 0 can be viewed as 0 times indicator omega. So this expectation of this quantity will basically be 0 times probability of omega, which is 0, right. And now so we have shown that this quantity over here, when you have empty set over here, is 0, and in that same way this quantity, okay, can also be shown to be 0. And since both the left hand side and the right hand side equal, okay, we can conclude that at least for the case where G is empty, these two things are the same, and one can similarly verify that this quantity and this quantity are the same when this empty set is replaced by your omega, which is the second element in your calligraphic G, and then conclude that indeed these two things are one and the same, right. So we verified first that this expected value of x is measurable with respect to G, and for every set in your G, one can actually conclude that these two things are one and the same. Alright. Okay, so this is what we have verified here for the case where you have omega. Okay, so let me just quickly go through it, right. We require that the conditional expectation of x with respect to G with respect to this must equal this expression, because this is how we had defined the conditional expectation. So this is what we have, and by definition this is expected value of x, and expected value of x can be written this way, and using our definition from of expectations of simple random variables, this is actually expected value of x indicator omega, right, dp, or in other words this is expected value of x indicator omega, and this quantity is basically expected value of x times probability of omega, which is expected value of x as desired over here, right. So we have verified this, and hence one can conclude that when your given sigma subfield is only made up of the empty set and the whole sample space, then the conditional expectation is actually the true expectation, right. Okay, so then there is this very important property of monotonicity, which says that if your x, given random variable x, is non-negative, then the conditional expectation will also be non-negative, right. So recall that this is a random variable and we are saying that this is non-negative, which means that if you look at every omega in capital omega, this left hand side has to be non-negative. However, as I told you, if two random variables differ only by only on a 0 measure set, then their expectations are the same. Hence it is possible that even though this is non-negative for every little omega and capital omega, the conditional expectation may be non-negative on every omega in capital omega except for a 0 measure set. Okay, so that's why this almost sure acronym is added to this statement over here, and this monotonicity idea can actually be generalized to the case where x is almost surely bigger than y, and suppose that x and y are in L1, so that the conditional expectations are well defined, and the monotonicity property says that if x is bigger than equal to y, then the conditional expectations also satisfy some relation like this in an almost sure sense. Alright. So we have seen some monotone convergence theorem for expectations. A similar monotone convergence theorem also exists for conditional expectations, and it is what we the way we would expect, that is, suppose you have L1 measurable random variable x, and in addition suppose you have non-negative random variables xn which monotonically increase and converge to x, then the conditional expectations also monotonically increase and converge to the conditional expectation of x given G. Of course all of this holds in an almost sure sense. Okay, so like we have a similar extension of monotone convergence theorem, we also have an extension of the dominated convergence theorem. So the dominated convergence theorem says that suppose you have a sequence xn such that every element in that sequence, that is xn, satisfies this relation, that is absolute value of xn is less than equal to z, and this should hold for every little omega and capital omega Furthermore, suppose that this z itself is L1 integrable, that is expected value of z is less than infinity, right, and because of this condition we trivially get that each xn is L1 integrable, right. Furthermore, suppose that your xn converges, right. So, unlike the monotone convergence theorem where we had xn monotonically increasing, here we are not insisting that xn monotonically increases, right. Here we are just saying that xn converges. So, it is possible that whatever the limit is, your xn's go up and down for different values of omega, but we are only insisting that the limit exists, and in that case again the limit and the conditional expectation operation can be interchanged just like in the monotone convergence theorem. Okay. So, the dominated convergence theorem says that if you have a dominating random variable, then the conditional expectation of the limit equals the limit of the conditional expectation, right. So, such a statement also holds when you have something like that, that is the monotone nature, and in that case this relation is referred to as the monotone convergence theorem. Alright. Okay. So, the next key property that we would be relying on is that of product rule, right, and this property since it is very important and we will often be relying on. Okay, I will prove this very explicitly and going over it a bit slowly, and I will also tell you or highlight the advantage of working with this measure theoretic perspective. Okay. So, what does the product rule say? Suppose x and y are two random variables and let us say they are both integrable. Okay. And suppose one of these random variables, in this case y, is g measurable. Okay. And the question is, given that y is g measurable, what can we say about the conditional expectation of the product, right. In one of the properties that we studied before, we did not have y, and we showed that if x itself is g measurable, then conditional expectation of x given g was x, right. In this case we are having two random variables and we are only saying that one of those random variables is g measurable, and the question that we are interested in asking is, what can we say about the conditional expectation of the product of x and y, and the claim is that this conditional expectation is actually y times the conditional expectation of x given g, that is whenever y is g measurable you can pull y out of this conditioning and write it outside. Is this okay? So, let us verify this property. Okay. So, the way we verify this, and in general the standard way of verifying several of the results in measure theoretic probability is to follow the following recipe. Whatever is desired to be shown, you first show it for an indicator random variable, then you extend it to simple random variables, then you extend the proof to non-negative random variables, and finally you extend the idea to general random variables. Okay. So, let us follow this recipe. So, the goal is to show this, okay, and towards that what we will do is we will presume that y has a special form, that is y equals indicator delta, where this delta belongs to g, right. So, by ensuring that delta belongs to g, we are ensuring that y is measurable with respect to g as required in the statement of this claim. Okay. So, now we have to show that if y has this special form, then this condition actually holds. Okay. So, let us verify that. Okay. So, the first thing that we need to verify is that this product is actually g measurable, right. Now, because delta belongs to g, y is g measurable, and this conditional expectation by definition is g measurable. So, we have a product of two g measurable functions, and hence the product is also g measurable. Okay. So, these are things that one can show using some of the discussions from random variables from chapter 5 of this probability path textbook. Is that okay? So, now it remains to verify whether if you take the expectation of this times indicator g or whether you take the expectation of this times indicator g, they remain the same. Is this okay? So, let us verify that. Okay. So, the left hand side, that is expected value of xy given g when it is integrated with respect to this specific g in calligraphic g, okay, by its definition, right, because this is a conditional probability, this must equal integral x y indicator dp g. Okay, so this is exactly what I have written over here by substituting that y equals indicator delta. Is that okay? Now because you have indicator delta, this delta can be moved here by introducing an intersection, hence this quantity equals the integral of x dp with respect to g intersection delta. In other words, this is basically the expected value of x indicator g intersection delta, right. But g belongs to calligraphic g and delta belongs to calligraphic g, right, and because this calligraphic g is a sigma field, one can conclude that g intersection delta also belongs to calligraphic g. Now since g intersection delta also belongs to calligraphic g, this this integral that we have will actually equal this integral from the definition of the conditional expectation of x given g. Is this okay? This just follows from the fact that if you have a conditional expectation, then this integral must equal this integral for every set in calligraphic g, and since we have shown that g intersection delta belongs to calligraphic g, these two things must be indeed be the same, right. So now what we can do is, whatever was there in g intersection delta, that intersection delta we can again move it above in this sense. So we can write it as indicator delta, and I have just written it here as y, and hence we have concluded that this expectation that we have here equals this thing, right. And since this g was arbitrary, one can conclude that indeed for the special case where y equals indicator delta, it indeed holds that these two things are one and the same, right. And the way we verified this relation, we can use the same proof technique to conclude that this relationship also holds when y is actually a simple function, that is y is summation I equals 1 to n ai indicator lambda I, okay, or delta I, where delta I belongs to g. Okay. So if y had this form, then one can conclude that such a relation also exists just by following the same proof, right. And then we can invoke the measurability theorem and monotone convergence theorem to show that if x and y now are more general, that is x and y no longer have any special form, but rather they are some general random variables which are non-negative, right. So then by measurability theorem, one can show that there is a sequence of simple functions that converges to y, and from the monotone convergence theorem for conditional expectations, one can then conclude that this also holds, right. And finally we can extend whatever proof that we have discussed here to more general scenario where both x and y need not be non-negative. In that case we just use this following idea, that we can express x as x plus minus x minus, and this x plus and x minus are non-negative random variables. Similarly y plus and y minus are non-negative random variables, hence if you look at x plus times y plus, x plus times y minus, and similarly x minus y s and x minus y inverse y minus, sorry, right. So all those four products are non-negative, and hence whatever we have proved over here, that will apply to that setting, okay. And one can show that in that case this property also holds. Is this okay? So this is something that is in some sense a standard recipe for working with conditional expectations, for proving properties related to conditional expectations, and in this case I sort of went over as many details as possible to verify one of these properties. Alright. So the next property, which is one of the again a very key property that we will be repeatedly using with respect to conditional expectation, is that of smoothing, right. So what does the smoothing property say? It says that suppose you have two sub sigma fields, in particular let us say you have g1, g2 and f such that G1 is a sigma field, G2 is a sigma field and F is a sigma field, and in addition G1 is a subset of G2 is a subset of F, right. And now suppose that X is a integrable random variable that has been given to you, and now if you do an iterated conditioning, that is you first take the conditional expectation of X with respect to G2, so recall that G2 sits over here, and then this is a random variable and you take its conditional expectation with respect to G1, right. So the smoothing property says that if you take this iterated conditioning, then that must equal the conditional expectation of X with respect to this smaller sigma field, right. So this thing over here vanishes, okay, and of course this equality holds only in an almost sure sense. And similarly, if you take this conditioning in this sense, that is you first take the conditional expectation with respect to G1 and then you take whatever you get its conditional expectation with respect to G2, right. Now this second property is very easy to show because this conditional expectation is actually G1 measurable, and because it is G1 measurable and G1 is a subset of G2, we get it for free that this is also G2 measurable, and since this random variable is G2 measurable, and when we take the conditional expectation of this random variable with respect to G2, we get back this. So the summary is that whenever you have G1 and G2, right, which satisfy some condition relationship like this, then if you do this iterated conditioning, then that will equal the conditional expectation with respect to the smaller sigma field, right. And we now move on to the last property that we will be repeatedly using in the discussion of conditional expectations throughout this course, which is that of conditioning and independence. Is this okay? So first let me tell you what independence means, and in this lecture I am going to define independence of random variables with respect to a sigma field. Is this okay? So what do we have over here? We have X, and I want to discuss when is X independent with respect to a sigma field, and I will use this notation to denote this independence. So we have a random variable X, we have a sigma field G, and we want to say when is X independent with respect to this sigma field. So we will say X is independent to this sigma field if for every A in the sigma field generated by X and every B which is there in G, we have this relation. So this relation is something very familiar to us, right. This is what is the definition for two events being independent. Now we are using this definition to discuss when is a random variable X independent with respect to a sigma field, right. So X is independent to G if for every A in the sigma field generated by X and every B in the sigma field generated by G, we have that A and B are independent in the usual sense, right. So in this case one can show that the conditional expectation of X with respect to G actually equals expected value of X itself. Is this okay? Because X is independent with respect to G, right, the best proxy for X which is G measurable is actually expected value of X itself. So with this we come to the end of this class, right. So let us quickly summarize what we have done throughout this week. In this week we have gone quickly over this whole textbook on probability path. In particular we have gone over measure theoretic probability, right, and this is one of the prerequisites of this course, and I wanted to quickly brush up some of the ideas and concepts that we will be requiring throughout this course, right, and since I wanted to brush up I have gone over it very quickly. In subsequent classes we will be going over we will going over the material very slowly. In particular we will be proving all the results in significant detail. Okay, so having said that, let me now summarize what we have done. In this week we looked at probability spaces, then we looked at random variables, then we looked at expectations of random variables. In particular we defined the expectation of a simple random variable, then we generalized to non-negative random variables and so on. Then we talked about properties of this expectation, and then in the last two lectures we introduced this notion of conditional expectation, and in this class we have discussed some properties of conditional expectation. In the following week we will be talking about martingale differences and conditions under which we can show their convergence. Having said that, thank you, namaste, and hopefully you will join me for the third week soon. Thank you.